Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. It's episode 13, which I called Memory Controller Woes because I've been bitching a lot on Twitter, essentially having a lot of issues with this generated memory controller on my Max 10 board. And I won't go super into detail here about it because, surprise, surprise, I ended up buying a new board. And maybe we'll still run into the same kind of issues, and I need to go through it anyway, but I think we'll end up avoiding a lot of the problems I was having. But essentially, the short of it was, my Max 10 board has some DDR memory on it, and it's DDR3, and in order to use it, you need to use some generated memory controller IP. Technically, you don't have to, but there's a lot of details about getting timing right to actually operate the memory at the right speed with a few different kind of clocks. There was like a read capture clock and a memory clock and the memory interface clock, and all those had to have the right kind of phase relationship, and there's clock crossing between all those different little domains and all kinds of very complicated stuff that is definitely beyond my very limited expertise with FPGAs. So I don't want to do that. On top of that, there's also driving DRAM and actually issuing the right commands to it at the right time, which is, I think that would actually be the fun part, and probably the part that I could do, because I think I could simulate that in a nice way and kind of, I know what kind of access patterns that I'm going to have, so I could probably make something optimized for that. And as a first implementation, I could just make something really simple that would always just try to just be really conservative about doing refreshes and just try to make that as simple as possible. And then at least we can move on, and then later I could come back and optimize. So I actually think that would be the easy part, even though that in itself is somewhat complicated as well. So there's just a lot of mess involved. And especially with this project, I'm really concerned with doing like a basic CPU and GPU design and an audio unit later eventually too. So I'm not that terribly interested about or terribly interested in driving memory and spending a lot of time on a controller to do that. So yeah, many reasons to justify using a generated controller IP. And so the particular board that I have here, this is the Max 10 development kit. There are examples on Intel's website about, because Max 10 is an Intel FPGA. There are examples on the site about how to generate a memory controller IP for this particular board, which is really nice because you need to enter some timing information that's based on like the lengths of the traces on your board and everything in order for it to be configured correctly. And it had all those settings in the example. But when I put that together, just the memory controller and nothing else, it builds, it seems to work, but then I noticed that in the timing reports for that project with, again, just the controller and all the recommended settings, it wouldn't meet timing. And as my design started to get more complex, this kind of became more and more of an issue. And I'm sure that there were other issues with my own design. So one of the things also is that the particular, this memory is DDR, so it's running at double data rate. And so to run this particular memory chip at 300 megahertz, which is its minimum, you need to generate a controller IP that's either half or quarter rate. And with this particular board, they only let you generate a half rate interface, which is 150 megahertz. And 150 megahertz, I think, is actually quite fast for this particular part. One of the things about Max 10 that's kind of a nice feature is that they have this, I think they call it instant on. And the idea is that the configuration, instead of being stored in a separate chip, a separate flash memory, it's stored, I guess, in the actual blocks of the FPGA. So it doesn't have to configure when you turn it on, at least as far as I understand. Maybe it's internal memory on the chip and then it gets configured. It doesn't really matter. The point is that the data is already on the chip, and so when you turn it on, it starts on essentially immediately. But a consequence of that, I think, is that it makes the logic blocks a little bit larger, which is of course relevant when you're trying to make a design that where timing is important. And I think that this was a matter of my own expectations, but I didn't really know how fast a typical design on FPGA like this would go. So what I did to try and make everything as simple as possible is the memory controller interface, the interface that exposed to me, ran at 150 megahertz. And I decided to avoid any kind of issues with crossing clock domains, which is, I guess, somewhat straightforward to do if you follow if you know the kind of pitfalls there are with doing that on an FPGA. And I read a lot of papers about it and stuff, and I enjoyed learning about it, but I also wanted to avoid it as much as possible. So I ran my system at off of the same clock as that memory interface. And I think that was a bit of a fast rate for the design that I'm doing. But the problem was, whenever I would compile my design in the memory controller, I would see these timing errors in the memory controller. And as I would change my design, I noticed that the timing errors would change in the controller, but it would never report errors in my design. So I don't know if I wasn't able to, or just didn't know how to constrain my design properly, such that it would be more relaxed about the constraints there, and trying to get the memory timing together first before it would, or like prioritize that over the other parts, the parts that were specific to my design. I'm not really sure. I did look into this feature called design partitioning. I think it's actually called blocks in Quartus. And the problem there is that that's not available in the free version of Quartus, so I can't even explore actually partitioning the design like that. There might be some floor planning stuff that I could explore, but it just didn't seem like that was the kind of issues that I wanted to work with, at least not yet. So I'd rather just clock my design down and then, for example, maybe use a FIFO between that and the memory controller, and then just have the memory controller work as is. But then what I did is I wanted to explore just like that. Just can I get the memory controller to meet timing and have a little bit of slack, so at least I can start from like a clean slate there and try to kind of isolate the problems in my design that way. And of course, the IP generator in my Quartus install somehow broke, and I don't know when or why. And so I updated my version of Quartus and tried to regenerate everything, and it still broke with the same error. Googled the error, and basically everyone, like, there's a lot of people that are having this error, and everyone would fix it with like re-imaging their machine. I went through my registry and deleted all the keys that I could find that were related to the old version. That didn't help. I was a little bit lucky, though, because I still have a Quartus install on my laptop as well. And that actually worked in order to regenerate the IP, so I could at least do some iterations on changing parameters in it. And with a certain configuration with like really bad performance, I did actually get it to meet timing just on its own. As soon as I added my own test, it would stop meeting timing again, which was really annoying. But it also, again, would give pretty bad performance for the controller itself. So I basically turned off. You can have it do look ahead for the commands that you're issuing. So if you issue a bunch of reads or writes that are going to be going to rows in memory that are sequential, then it will batch those and it'll be able to do them faster. So you end up with better throughput through the controller, which is the kind of thing you want to do. So anyway, it ended up being this really frustrating process, and in the end, I got a controller with like worse performance that I couldn't even tweak on my main machine. And I talked with some of the guys at my work that do FPGA stuff professionally, and they were just saying, like, sometimes you can get these boards that they'll give you like this example, and it'll be like right on the edge of the kind of performance that you can achieve. And that sounded like what was kind of happening in my case. And maybe it wasn't. Maybe it was just me not knowing enough of this stuff to really be able to debug this properly. It's probably a combination of the two. But what I decided to do is I'm going to get another board. I feel like I'm doing this kind of on hard mode, and I don't feel like my design is that complicated. And if it is, I would at least like to be able to eliminate variables and try and simplify things. So one of the things I did is I went and I just removed the memory controller, and I'd used all in internal memory. And this is before I got the new board, so I was still on the Max 10 board. I removed the DDR controller, and I replaced all of that memory with block RAM, which is inside the chip itself. And the nice thing about that is that then it's very clear if my design doesn't meet timing. It should also be a lot easier to constrain the design and make the tools handle that properly. And in that case, I did actually still have some timing issues that finally appeared in my design, running at 150 megahertz. And I think a lot of those actually came up as a result of switching to block memory, because I think that has to be distributed around the chip now. So I think there are some constraints that made that a little bit different. But anyway, I was able to fix that just by reducing the clock rate, because I don't even need the thing to run at 150 megahertz. The only reason I was doing that was to interface with the memory controller without doing clock domain crossing. So I dropped it down to 100 megahertz. But then the other consequence of this is that now the system has a 160 by 120 frame buffer in order to actually fit 2 buffers in memory. And so I kind of retimed the design to actually work with that. So the nice part is I have a working design now on my Max 10 board with no timing errors. It seems to be super solid. And I think that's a good starting point for moving back to the other board. Because what I was trying to do is just like isolate any problems that I could have, because what if I'm not constraining my design properly or not doing timing right or something else? If it's anything else, I at least wanted to know. But now it looks like it's okay. But in addition to that, what I did is I just went back to basics. So I opened up Cordis and just like made the most basic project I could. Worked on building a reset synchronizer to like play with that. I worked on doing the design constraints as best as I could to just like eliminate all kinds of warnings and errors that I could. And I successfully made a design that did that. And all it does is blink an LED, but it's like going back to basics and just setting everything up from scratch. And I was at least happy that I was able to do that and get rid of all the warnings. But I haven't had a chance to go back and do that in the Xenoing project again. Because my new board arrived. It came a lot quicker than I thought. It took like 5 days. So I have that here, and this is now a Xilinx board. So I spent a lot more time doing that same process. So I got what I have open here is a project where I'm just, again, blinking an LED. But I went through and I just kind of learned a few different things. The other thing I did, I forgot to mention, is on the Max 10 project where I was just doing everything bare bones, I also learned how to use a PLL to generate a specific clock frequency. So I was playing around with the clock frequency and seeing kind of how high I could go, and that was kind of fun. But again, making sure that I did that in combination with having proper design constraints to, just get a feel for even putting together some of these basic blocks. So I also did that in this Vivado project as well. So I just want to kind of walk through a little bit of that, which I think will be specifically helpful for Daniel Collin, who is about to receive the exact same board and probably is going to go through some of the same stuff. Hopefully when I finally get to doing a memory controller on this board, it's not going to be nearly as difficult. And it looks like there are a lot of example projects from Numato. So I let me pull up the board that I have. I can show it, but I don't want to unplug it, so I'm just going to pull up pictures of it. This, again, Daniel Collin actually found this board, by the way. And so this is it. This is a Mimos A7, I think you say that. Some moon of Jupiter or something. It's on sale right now, by the way. So I think this is a really good price for this board, by the way. It's an Arctic 7 chip. Pure FPGA, no like hard processor or anything. And it's also got some DDR3 memory, I think. I think it's twice the memory of my other board. I think I'll be able to run this at faster clocks. I think the generated memory interface, all the examples that I've seen run this at 200 megahertz instead of 150. We'll see if that's a problem. But at least now I know how to do design constraints for constraining all the inputs and outputs. And at least then if timing issues arise, I should be able to deal with them. But we'll see. Hopefully that's not going to be an issue. Still has UART to USB, so that should be easy. Although I haven't... it also uses that for the programming interface, so hopefully that doesn't conflict or anything. It's also got these HDMI ports, and as you can see here, and a bunch of switches, bunch of LEDs, all kinds of stuff. Reset programming switch. It's got Ethernet, and it's got a lot of GPIOs, which is why he was looking at it. Anyway, it seems to be a nice board. It was really easy to kind of plug everything in and make it work. That's exactly it, Alkama. By the way, hi to guys in the chat. Try later, Quark Shooter, Desius, Daniel Collin, Alkama. And thanks again for the sub, Alkama. Appreciate it. One of the differences, by the way, on this board is that it does have actually HDMI in and out. But if we look at the HDMI ports, these aren't transmitters here like they were on the other board. These are actually just buffers. So we're going to have to do that. I think it's TMDS is the protocol. the HDMI uses. I'm gonna have to do that by hand, but again, there's example projects for that, so I want to look into that. But essentially, now that I'm gonna be targeting a different board, or at least trying to, there's gonna be kind of a somewhat long process, at least probably a couple weeks, where I'm just like making very basic projects to kind of interact with all the separate pieces on the board. And I like to do that as individual projects, just kind of throwaways, where you just kind of make one thing do a little bit and then just kind of move on, and then putting everything together becomes a lot easier later on. And so far this has been easy. Again, the project I started with, it's called LED Shiz, and it's only got a couple things in here. Actually, it looks like, oh no, this is still there. Let's see, I'm going to close some of this stuff because I just want to look at the source here. Yeah, so I have my top level module here. Let me zoom in. Can I zoom in here? I don't really know how to use Vivado, but I'm also kind of forcing myself to use the tool as it is, just to kind of get a feel for this, because you can't just ignore using these tools with this kind of stuff. I've learned you just have to fight with it sometimes, but it should be fine to like generate code that then this just uses as kind of a tool for compiling and everything, so it shouldn't be too bad. But anyway, I've got my clock in, my reset, and my LED. So my clock in and reset are inputs, and then my LED is output. I found out apparently I need to do var and logic here. I need to brush up on my system Verilog to find out why I actually need that. In fact, the logic might not be correct here. It might be that wire is actually more correct here instead of var logic wire. I'm not actually sure. I need to brush up on that, which is another good reason to do simple projects like this. Hey, Drew, too. Did I already say that? Anyway, hi. Oh, by the way, didn't call in. Is it 2 gigabytes, by the way? Because that's a common thing here. Yeah, it's gigabit, I think. A little lowercase b. I'll get you with that. Finrog. Yeah, it should still be more than enough for the projects that we're intending to work on. So not worried about that, but yeah. Anyway, this input clock, I piped this into this MMCM, which I guess is something like a PLL, but essentially a clocking generator. So if you go into this IP sources thing, I have this MMCM, and I can pull this up. And this, you just go through a wizard where you kind of customize what you want the IP to do. But the whole point of this is that you give it some input clock, and it knows you specify the frequency of that. And I know that this is 100 megahertz because that's what the oscillator on the board is. And then you can go to the output and then specify the particular frequency you want. And if this is out of bounds or something, they're gonna tell you. You can also adjust like the duty cycle and everything. A couple other options, I think. But essentially, yeah, you can like adjust the reset. I also have an output here for when the frequency or when the clock is actually locked to the input. So when you actually get the right frequency. And I end up using that as a reset. I'll be right back for 1 second here. And we're back. Thanks for the sub, Finrog. Really appreciate that. But yeah, you can specify a lot of options about the clocks. And so it has this reset that's assumed to be asynchronous because you usually have like a reset button on the board. In this case, whenever that's pushed, I want to reset the chip-to-node state, and that's what this reset's going to be. And then the input clock, and again, the output clock is specified. And there's actually a couple that this can generate. Looks like it can do 2 with this same module. And I guess if you needed more, as long as the chip has more MMCMs or PLLs, that you could instantiate more of these. But yeah, then you have the output clock, and then a line that says when that's locked, and that I think that signal is synchronous to the clock output here. So that should be safe to use. So then I just instantiate that here in the Verilog code just by referring to it by name, because you also say what you want this module to be called, so that's easy. And then after that, there's this reset synchronizer. So this is kind of an important thing. And you'll read a lot of papers about this if you look into this. So with FPGAs, I actually don't think you always need to have a reset functionality at all. If you know you're targeting a given FPGA and you don't necessarily need to use the reset, because you can always power cycle your board. So this is kind of not necessarily something you have to look into, but I think it's a good idea to design that way anyway, because also having resets like this is good if you want to do some simulation. And if any of this ever moved to ASIC, obviously you'd need some kind of reset stuff. But the whole thing here is that a synchronizer, there's a lot of papers about this, especially from this company called Sunburst Design. They also have a lot of really good papers on metastability and crossing clock domains, which is a lot of really interesting stuff to read, but it's still a bit over my head, of course. Anyway, the whole idea is that the problems with a reset is that... Actually, let me explain metastability a little bit. I think I've described this on my channel before, but it's always fun to talk about. So when you have a flip-flop, this is my flip-flop, we have D, which is the input, we have Q, which is the output, and then we have the clock input here. And this basic flip-flop has a very simple behavior. If you have D, let's say D does something like this over time. And then we have the clock, which is going to be rising and falling at a pretty regular interval here. Essentially, the behavior that a flip-flop has is that on every rising edge of the clock, so here and here and here and here, then D goes, or Q reflects D, is how we would say that. So if we graphed Q, let's say it were low on reset, then here it would still be low, and that would hold that value even as this changed until this clock edge, in which case it would sample the high, so Q would go high. And we're going to keep going until this edge, and it would still be high, so we actually missed this low pulse, which could be a glitch, it could be anything. And then that's going to continue until this one, where it would be low. And this is really fundamental for making logic circuits that actually work, is this kind of synchronized sampling of the inputs. So this is our flip-flop or our register. Register is typically a D flip-flop, which has this kind of interface, and sometimes you also see the inverted Q just already available there, but you could also get that by sticking an inverter on this. So it really doesn't matter how you want to set that up. But anyway, this is all fine, except there's something really strange that happens when you have this case. Let's say this was D, and this is our clock. So the issue is that internally, these flip-flops are usually implemented by like this little feedback network. Now I can never remember if I think it's NOR gates, which means I think I drew this wrong. I don't remember the kind of gates is the typical SR latch, but you can probably look that up. But the point is that this is something like you have this kind of network like this, where you have, I think this would be your set and your reset, and then here's your Q and your Q naught. Something like that. Now, a flip-flop is a little more than this because you need something to detect the clock edge that when it will actually latch the new value, and a couple other things. But the point is that this state is actually held in this little feedback network. Finrog, it was supposed to be inverted, but I'm probably wrong about that. I can never remember. But the point I'm trying to make is that you have this feedback, and it's the feedback that actually holds the state. And because it's feedback, and these are actually analog signals at this level, an issue happens if the data changes too close to when the data is being latched. You can kind of imagine it as you're holding one of these lines, and then as the feedback is settling, you suddenly change what the inputs are. And so instead of Q going like this, which is what we want, we actually can get something like this, where it's like some in between level, and it will either end up being low or high depending on what came first, which one of these edges comes first. And I do think that the behavior here is, it's non-deterministic. Like I think it will always settle to low or high, and it depends on which edge comes first, and it can also depend on noise, which is really annoying. But the worst part is that the closer these two edges are to each other, the longer this period of this metastability can be. And I don't think we really can know how long this will take. This could be, ideally, it's at least less than a clock cycle, so we can kind of work around this. And then on the next clock, we would ideally get a good level. But yeah. So the problem with this is that when you have resets, because a lot of the time you also have like a reset input, which is often called clear, that this basically overrides this edge. And I should mention, actually, before I talk about clear, that this sort of time for safety around this clock edge, we have what we call a setup time. This is the setup time, and this is the hold time, TS and TH. And the idea is that if you need the logic level coming in on D to be stable before TS, and then you need it to still hold that value until after TH. If it changes at all within this, then you can have this metastability phenomenon. And so timing analysis is really important when you're actually designing these circuits, and why you get such weird kind of non-deterministic behavior if you don't meet timing. But the nice thing is that it's actually pretty simple to, like, between a set of flip-flops, where you have this flip-flop here, and this goes into another flip-flop, and you have some logic in between here. I mean, you know the setup and hold times for here, you know the setup and hold times for here, you know when these clock edges are going to arrive at each one of these registers, and so you can kind of figure out how far away these need to be and kind of adjust that. And the tools will do all of that for you, as long as you constrain your design properly. And if all of your logic is sort of in the box, if the Verilog synthesizer and everything can see all of your logic, then this isn't a problem because it will understand the constraints. But one of the constraints you need to give is how fast is this clock rate. The part on your board doesn't know, right? You know, because you know the external part that's going to feed the clock into your device. You know what that's going to be, and so you need to tell the tools what the speed of that clock's going to be. And there are many cases where if you do certain things here, for example, I have this clocking module, and I actually don't need to specify, or the only place I need to specify the input clock frequency is here, and I don't need to specify it elsewhere. Even though in another design, if I didn't use this clocking module, then I would have to specify that elsewhere. So most designs have these constraint files, which I know I'm jumping around a lot, but kind of important. And here you would normally specify that. So you'd say something like create clock, input clock, and then you'd say like the period is 10 nanoseconds. That would give you a 100 megahertz clock. And then I didn't write this totally correctly, but it doesn't really matter. I think you would do like name clock in, and then you do on the ports. And then what this says is that on your top level module, there's a port that's called clock in, and whatever the input to that is, which is going to come externally, is going to be a clock with this period. And then in the rest of this constraints file, we're going to refer to that clock under this name. And so then when the tool is going to be doing placing and routing and all that stuff, it's going to know how fast that clock is, so it's able to do this kind of setup and hold time analysis. And so it's going to try and lay out your design such that it satisfies those constraints. And if it can't, it'll tell you. And that's really good. We want that. But there's one other case where this is a problem, or actually there's a couple. The other things that it's not going to know about are the inputs and outputs to your module that go to actual pins on your chip. So you need to constrain those as well. And the other thing is, coming back to this reset stuff, when you push that reset button, that's not going to be synchronized to this clock, because it can't be. It's an external signal, and it's going to happen when you push the button. It's probably going to bounce a lot when you push the button. So what we need to do is we need to essentially all external signals that come into the chip like that, we need to synchronize them to the clock. And so for resets, that's particularly important, because just with these setup and hold times, the clear signal also has these similar constraints. So instead of the data changing during this period, there's I think it's under a different name for resets, and I think it can be slightly different. But there's some period where the reset can't happen within a certain period around the clock edge as well. And I don't remember what the parameters for that are. But again, we don't really specify or care what the actual parameters of the flip-flops are, because that's internal to the FPGA, and the FPGA tooling knows what all that is. So we just need to specify a couple things. One of them is that in this particular constraints file, I've said that the reset is actually going to be what's called a false path, which means the timing will not consider any of that. So as it's coming in, we have sort of my top level module here, which is like the LED thing. And so the output is the LED, and the inputs are, I wrote that really bad, but that's fine. The inputs are the clock input and then the reset. And what I've basically told the tools is that don't even consider the reset stuff. And I'll get to how I'm kind of getting around that. And then that way it will ignore that in the analysis and just kind of lay out the design based on the actual needs of the design, because this is going to be an asynchronous signal anyway. But that doesn't actually solve our problem. That just allows the tool to ignore the timing of that signal because it can't know it anyway. The other thing that we need to do is we need to still make sure that once we get a reset that actually feeds into all of our flip-flops, that reset signal isn't going to be raised within any of these periods near the clock edge that are going to cause some trouble. And so the way we do that is actually fairly simple. We use what's called a synchronizer. And this is a general thing you need to know when you're going to pull any signals into your chip, is how to synchronize those to your clock. So again, I mentioned this issue of metastability, where if you get something changing, so there's a lot of cases that can happen here. Let's say this is your clock. Now, if your data, if your incoming data, if that incoming pulse is stable within whatever this period is, and this can include your reset or whatever, then there's no issue. So if you get a transition on your data here, it's not a problem. If you get a transition here, it's not a problem. And the direction of the transition doesn't matter either, as long as the signal is stable during this period. So I meant to draw this out here. Then you're fine. But if it ever happens in there, then you get this weird phenomenon, which is the metastability. And then that's either going to end up at 1 or 0, depending on the order of events, and you can't actually know that. So statistically, this is going to happen eventually. And like on a reset signal, you're not doing resets that often. You are doing them every time you turn on the device, but it's not that often. And so this may never happen if yeah, Daniel calling him. Luckily, when I get to the solution, you'll see that this is like, I should have said that this is a very manageable problem. You just have to know it. So I think it's a very interesting phenomenon that happens. But the point is that if there's any signal that you want to synchronize to your clock, because like obviously once this metastability thing happens, this can also, like, let's say the output of our flip-flop started going like this. Well, maybe this feeds into another flip-flop, and then that starts going metastable, and then your entire state of your design is essentially compromised because of this one bad input. So this is statistically going to happen at some point, and you can't really test for it. You can't really know what's going to happen, but it's a very manageable problem because we know statistically that, well, it's actually very, very unlikely that this is metastable for longer than a clock period or longer than 2 clock periods, for example. And we also know that this will settle to 0 or 1 eventually. We just don't know how long it'll take. So the way we manage this is by using what we call synchronizer chains. And the way you do that is let's say you have your input. In this case, it's a reset, but it could be anything. So I'll just write in here, and we do a couple registers. And I'm just using this little clock thing here as a symbol for register. You'll see that a lot. And you just have a chain of a couple of these. And so then this will be in sync. Bye. So this is your clock that feeds into here. And this is the same clock that the rest of your design is going to be clocked to. So like eventually, of course, you're going to have some other logic that is also using this clock, and then that's what this will be sort of routed to. And the whole point about this is that what's going to happen here is that this signal could very well change near one of the rising edges of your clocks. So essentially, you're going to get, like, statistically speaking, you will have metastability problems here along this or not this line. This line here can have metastability problems, but it's extremely unlikely that metastability will actually last an entire clock cycle. So you might, let's say it was transitioning from low to high near the clock edge, and the output you saw kind of goes high and then settles back to low, but it probably settles before this next clock edge. That's kind of the idea. And then it's still low again. Or actually then, by that time, because the input did this. So at that time, when you sample this, it'll be clean and you'll be fine. Or the alternative is it'll do this and then kind of snap to high before the next rising edge of the clock, and then you're fine too. So the whole point is that it's extremely unlikely that it will actually happen for as long as your clock cycle is. Again, this depends on how faster your clock is, but it's rare that it lasts longer than a clock period. That's kind of the idea here. So then you're going to, statistically speaking, have metastability problems here, but it's very, very unlikely that you'll end up with them here, because this input should have stabilized by the time you get the next one. Dan MP87, thanks for the sub. Really appreciate it. So that's kind of the idea behind synchronizer chains. Now, of course, it is possible that this metastability happens for longer than this clock period. How do we fix that? Well, we add other registers here. We make the synchronization change, or we make the sync chain longer, is the idea. And that probably sounds really crappy. Probably sounds really like a cop-out. But it's actually good. Like, this is proven to work. And it's one of those things where if you say this is astronomically unlikely, like let's say this is 1 in a 1 trillion chance, then the likelihood of that happening and then that output of that also being metastable for another cycle is that whatever that probability was squared. And you can make this chain as long as you want. But you would typically have just 2 for a lot of the designs that we do in FPGAs, I guess. Again, there are papers about this that know a lot more about this than me. But that's kind of the idea. And then this works. There's something called mean time between failures, MTBF, and there are a lot of tools that will detect, for example, the Vivado or Quartus tools will detect that you have a synchronizer chain. Because this is kind of an obvious pattern where you have 2 registers where just one's fed into the other. They're both on the same clock, and then the input is probably a false path or something that we don't have timing information for, and then the output is synchronized to the clock. That's a very easy pattern to recognize, and you can calculate based on your clock rate and how this is hooked up on the actual device. It'll calculate the mean time between failures, and it's usually several, like I think a really long time. In fact, I want to see actually if we got that here in this implementation. So if I open the implemented design, I made some change here, but that should be fine. Yeah, the tools will calculate it for you, and they should tell you what that mean time between failures is. I mean, you still need to add the synchronizers, and I'll get to how often you need to add them, because the short answer is I don't know 100%, but I do want to talk a little bit about that, and hopefully we can reach a consensus. I'm sure this is going to come up in the Games Tech Slack at some point. Was it Dom Fias who's also active in that channel? He was talking a lot about that yesterday. I was asking him if he was adding synchronizer chains to the data path or just the control path, and I'll get to what I mean by that as well. And he said he wasn't doing it on the data path, and I've actually read that in a paper as well that you don't need to. So we'll get to that, but so I'm actually a little bit disappointed that I'm not seeing it here. To be honest, I don't really know where to look in the Vivado tool suite yet. Here we have async stuff here. From clock to clock. That might be something else. I'm not sure. Oh, here it actually. This is the reset synchronizer. Oh no, this is just my synced reset signal going to all these clears, and it did analysis on that said that was correct, which is nice. Maybe I'll open up Quartus because I want to find out what it told me, because I know it told me this in my other test. It calculated what that was, so I want to see what that is. But yeah, so the one of the implications of this, of running a signal through the synchronizer chain, is that the soonest you're going to see a change in this signal is however many cycles there are registers here, right? So you're going to see that change at least 2 cycles later. Now, for the design that you're going to be working on, where you're going to be interfacing with something that's like 7 megahertz, and you're probably going to run the FPGA at like 100 or more. That's not going to be an issue. You're not going to miss anything by having a delay of 2 cycles. But I think, and maybe I should pull up those papers, because they go into a lot of interesting stuff about this. But I really want to see where this calculated this. Constrained paths here. Because it does this. Yeah, so here it said report metastability found 1 synchronizer chain. The design MTBF is not calculated because there are no specified synchronizers in the design. So maybe it does say worst case available settling time. Okay, so it didn't actually calculate it here. Fraction of chains for which they could not be calculated is 1. So I guess I would need to figure out how to get it to calculate that. But I know just from all the designs I've seen, and also all of the papers I've read about it, that 2 is the default. And if you search metastability and synchronizer chains, you'll find everyone's just doing 2 or 3. I found these one slides where they had this Borat doing thumbs up when there was 2, and then if you're still worried about that, you can do more, and then it just showed multiple of him doing this in a row, like kind of analogously to adding more registers in the chain. But it just seems to be one of those things where this is good enough. And yeah, let me find the papers. The sunburst design. Now, one of the things I talked about with resets is that it's actually not a problem that the assertion of the reset. So if the reset goes high near a clock edge, it doesn't really matter, because the reset's going to be high for a while, and then everything's kind of going to settle out. But actually deasserting the reset when the reset goes low, that needs to be synced to the clock. Otherwise, you'll get metastability after everything's been reset, and then you've potentially ruined all the advantages to having your reset. And so actually I want to look at the code to my synchronizer here a little bit. Which literally all this is that there's these 2 flip-flops, and then whenever the reset happens, we just set the outputs to 0. Because this is an active low signal in my design. That's pretty typical. Bowspot, what's up, man? And then otherwise on the clocks, then we use this syntax to just kind of shift this high value through the 2 flip-flops. So it'll go into FF1, and then on the next cycle it'll go into FF2, which is what our output is. And we can see in the schematic as well. If we go in here, here's the synchronizer. So here's my input for the reset, and there's the clock. And the clock coming out of the module is the one that we want to synchronize the reset to. So in the reset synchronizer, here's the whole thing. I also use this locked signal as another reset coming out of the PLL, which is just fine. But the point is that we have this asynchronous clear, but then the output of this, you can see that this input's tied high, and then that will go through the 2 flip-flops after this reset has been synchronized. So these are the synchronizing ones, and this is the path where that metastability can happen. But that's fine because it's between these 2 registers. So this is the synchronizer chain in this actual design. And then lots of other stuff for what was a 32-bit add. It's kind of funny that it gets expanded like this in this schematic view, but it's actually also good because you can see the specific LUTs and all the different registers for the different bits. And you can click on these and get where they're mapped to in the device, which is quite cool. I guess it was down here that ended up. It's that register. I think that's really cool that you can see all this. Gives you a very, very fine-grained view of this, actually, which is really nice. More so than I expected from this tool. Anyway, let's see. Sunburst, asynchronous resets. I want to just link a couple of these papers because this is the one about resets, which there's a part 1 to that too, but you don't really need it. So the one that I think is most interesting is there's this simulation. It's this one here, which is actually from the year prior. And this one is a paper about simulation and synthesis techniques for asynchronous FIFO design. And I just read this because I was curious. Because one of the things you can do is I mentioned that you have this metastability issue when you're bringing in anything into the FPGA, but you also have the same issue when you have different clock domains. If you have this part of your design hooked up to 150 megahertz clock, and even if this is in the same chip, and then this part of your design at 50 megahertz, then these clocks are probably going to be out of phase, even if they're very close or one's just a multiple of the other one. There might be trace length differences between the different signals, all kinds of stuff. So it might be really hard to guarantee that those are actually sort of synchronous with each other, even inside the same chip. So these signals that go between here also need to be synchronized. So you need a synchronizer chain in here, and you'll need a synchronizer chain in here. And also typically to make this delay as long as possible, you also will do registers on the outputs of these. So you'll have some logic that outputs the value you want to send here, and then on the next clock, it will go here, and then 2 of these clocks later, it will actually get that signal. And the same thing here. So a bit of latency there. But again, if this is all in a FIFO, then you'll still get pretty good throughput through that FIFO, even though you have these few cycles of extra latency through that. And also generally, a lot of these like IP generators for a lot of these FPGA tools will of course have FIFO designs that you can just grab. So I need a FIFO of 32 elements, and they need to be this many bits wide, and they're going to be on separate clocks on the inputs, and then it's easy to hook up. And and that will also have the right constraints for all the timing analysis and everything, sort of built in and done for you, which is really nice. So if you're used to multi-threaded programming with FIFOs, then this is obviously not really a new idea. So that's a good way to cross these clocks. But coming back again to the talk that I had, and also this paper, and why it's kind of interesting, is they talk about how do these FIFOs actually work, because there's some interesting things about trying to, again, knowing that metastability will happen within the FIFO, how do you make that safe? And a lot of that is just like logically, well, if metastability happens, then if we use gray codes for translating how much of the FIFO is full or not, gray codes will only change 1 bit out of the entire value for every clock transition. So that really helps to avoid metastability, just because you only change 1 signal at a time. And on the other end, if it didn't capture that change because of the metastability issue, you either get the previous value or the next one, and both are safe to assume that, like, because of the way FIFO works. If you're being sort of pessimistic, then if you have the previous value, then you're still safe if you don't have quite the updated value. So like the consequence of not knowing that someone just wrote to the FIFO is that you still assume it's empty, so your FIFO is safe. And same if you don't know if the other end read, then you just won't write into it if you think it's full. So there's a lot of like those kind of ways of getting around it logically, but then also there's some cleverness about how you actually transfer stuff. Because this is actually one of the bigger problems that I don't think I mentioned, is that when you have multiple signals coming in, so let's say you had a clock and 3 data lines, and these you need to synchronize into a certain clock domain. The obvious solution would be to do these synchronizer chains on each one of these bits. And this doesn't work, by the way. And the main reason is because let's say the clock goes to all these. But the issue with metastability is how close do the transitions here happen to the rising edge of this clock. And the problem is, you might, even if you had these trace lengths perfect in your design tool and you had everything nice and you did all your timing, it's still not going to be entirely perfect because there's different small variations in the chip, all kinds of stuff. So it might be that, let's say if this transition from the number 3 to the number 4, which would look 100 instead of 011, or 4 to 3, then you have multiple of these bits changing for that clock, and then you might get one of the bits is captured and one isn't by the time you get the value on the other side of the chains. And that's obviously bad, because then you get bad values. And again, like gray codes and stuff can do that, but you don't want to be using gray codes to encode everything, because that's, again, only safe if you're going to just increment the value. These values could be anything. So there's some really interesting things that they do where they actually just only put these synchronizer chains on the control lines. So in this case, you would do this for like the incoming clock. And then the data lines you just pass through. And essentially what you have here is these end up being sort of multi-cycle paths, because what will happen here, let's say you want the clock to be output here, and then you just have some registers here. I'm kind of showing this as like time. So I don't think you do another register here. I think actually these should be aligned with these ones. And so the idea is that if all of this sort of changes sort of at the similar time, these will have an extra cycle to settle. And this is actually okay, because you won't sample these values. So I think actually I'm drawing these wrong, and that this here should actually be some kind of gate where you have the input and then like an enable. And the enable, it comes from part of this stuff that's inside this clock domain already. And then this is the actual input. And then this is the input to the flip-flop. So you only accept that value when some synchronous signal says that that's okay. And if that synchronous signal is based on this synced signal, then these will have enough time to settle by the time you actually latch the data. Once you've sort of decoded that the fact that there was a change on this synchronized signal. I know it's a bit complicated, and part of the reason is that I am not an expert in this at all. I'm just trying to kind of wrap my head around it in general, but that seems to be the case, that you can, if you set up your data path such that you're not actually sampling any of the values that could become problematic, and you know that these values are going to be stable while your synchronized signal is stable, then it seems to be okay to not have synchronizer chains on these. And in fact, it's better to not have them on there, because otherwise the synchronizer chains could capture different parts of the value, which could be really bad. Now, again, I wish I knew more about this to tell you, but I don't. And to be honest, I'm not entirely sure if what I drew here is going to be safe, because I don't know if this gate can glitch if this is transitioning, or if this is not a proper logic level. Even though this other one is, does this and still behave as an and? I don't actually know. So there's some design sort of considerations there that I just don't understand. So it would add some latency to your design. Essentially, anytime you're crossing a clock domain, or when you're synchronizing any signal into another clock domain, it will add latency to your design. And then there's also, you need to be very careful when you do it, because you need to make sure that stuff like this is safe. So you're going to have to do some research there, and I would be very interested in learning a lot of this. So what that Domfius guy had, I actually want to pull this up. I hope it's okay that I share this. I assume it is, because I think he's doing all that stuff in the open. Yeah, I had the sense that you had no idea about it, Daniel Colin. I mean, I didn't either until I got into this, and I went nuts when I figured it out, because I was like, how does anything work? But these do work. So what he's doing is he has these different clock domains here. And so here he has this 81.25 megahertz memory controller interface, and here is his 100 whatever megahertz SoC interface here. And so here he's doing a read. And so he sends this read issue signal here, and here it crosses the clock domain, so there's probably latency here. And then he waits until he gets like an ACK signal back. And so these signals would be subject to those delays. Each one of these, there would be a synchronizer chain here, 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 and here. And he's essentially doing this really kind of high latency closed loop solution that should be really safe, but he's going to have synchronizers on all those. But what was interesting is he only did synchronizers on these on these sort of control paths. On the actual data that gets latched that he's sending either way, he didn't do any synchronizers on. And that apparently worked. I would love to read more about that, because I also know that Obviously, he's a very clever guy, but I don't think he's an expert in this domain either. I think a lot of us in that channel are kind of trying to hack this, which is really fun because I feel like we're all kind of in it together in a way. Iron sharpens iron or whatnot. But yeah, I want to be more sure from experts in this field that that's a safe thing to do. So the general consensus is be very careful if you're crossing clock domains, and that includes pulling inputs to your chip. Now, sending outputs, don't worry about it, right? Because that's the other side's problem. And there you might have to specify constraints on your output pins to say like, well, we need this kind of timing relative to our clock such that you don't have a lot of skew between the different signals. So you need to specify that as part of your design constraints, which again, if I pull up this constraints file, I specify that on this output. So I have this LED output, but what I do here is I also mark this as a false path. So I have this dummy set output delay, and then I mark it as a false path because it's an LED, so we don't actually care about the timing. But if this had been an input to the HDMI transmitter, for example, then we want to make sure like the clock that we're sending out is roughly in phase with all the other data signals. So you want that to be specified more accurately. So typically you'll specify the sort of min and max output delay that you can tolerate for a specific output pin. And then the nice thing is the tooling will just figure all this out, because the math to figure this out for one path is really easy. It's just like that setup and hold time is a constraint on both sides, and it's pretty easy to figure out given all the knowledge that the tools have. And then of course solving that for many of these paths can be really difficult, and if your design has really long paths, it might be impossible. But it's going to do its best in the synthesis and the place and route, and then at the end it's going to do a timing report on the actual design after it's done its best, and it'll tell you if there's problems. So I guess what I'm trying to say is, and what I wish I had done when I started getting into FPGAs is I just was like, well, let me write some Verilog and let's figure this out. And for very slow designs, that's probably not really a big deal. But even for designs of just above even pretty basic complexity, you need to at least be able to specify these constraints and check your timing reports, because they're going to tell you if your design is going to just completely break or not. And that's also why I was so frustrated that memory controller always had issues. It always reported errors in the timing because I didn't know if those were benign or not, because they might be. A lot of the times when the tools are doing timing analysis, they're being conservative. They might do timing analysis assuming the chip is running at like beyond its regular operating temperatures. If it's too cold or it's too hot, or you have some weird process variation, and it's going to try and simulate all that, because of course this stuff changes with temperature and everything, and also so it's kind of complicated. But so it's really frustrating when my design would sometimes not work, and I'm quite convinced that was the reason. I don't think it's logic errors because I verified the logic in the Verilator sim, which of course the Verilator sim doesn't actually simulate any timing related stuff anyway, so it's only simulating the logic. And then there's of course ways to also write Verilog so that you generate primitives like latches that have timing problems sort of inherently, but that's actually fairly easy to avoid. I don't think I've made any of those mistakes either, but I might have. But I don't think so. I think it was always timing when this was actually an issue. And so it was really annoying when I would always get those errors no matter what I did, because I didn't know if what I had designed was going to have a problem or not. At least I couldn't eliminate that. So starting at the beginning and at least learning a little bit about how to specify these constraints and what kind of warnings you get when you don't do it properly is going to be a good investment of your time. But again, this super simple design here, I just have this clocking module, and then I have this reset synchronizer, which synchronizes the reset input to that clock. And then everything else is just as simple as it can be. So I have this LED register and a counter register, and on all the rising edges of the clocks, I add 1 to the counter. If the counter is this value, which means on the next one, it would have been, in this case, 1 million, because I want my LED to do a full on-off cycle every second in this case, and I'm running at 200 megahertz. So if the next value is going to be 1 million, then I invert my LED register and I set my counter to 0. and that's it. So the rest becomes really basic, and then here it's reactive to the reset as well. So, and this all seems to work, and I've silenced the majority of the warnings in the design. There's a couple here that still pop up because when you're doing this, you have synthesis, which is going to take your Verilog or whatever and actually give you a hardware model, and then you have implementation, which is going to do all the place and route and everything. And in synthesis here, I do this thing where I rename. This is really common, by the way. I take this generated clock, the output of this clock module, and I name it clock such that I can then use that name in the rest of the design constraints. And it gives me errors actually that this was not a proper path in my design, which is where the pin is that clock is coming from. And I got that from the tools. It also says that this clock is not found and that these constraints are bad, but these are in synthesis. And apparently that's fine as long as they don't happen in implementation. If we look at the project summary, it says out of date now because I was saving changes to this file, but it does work. It says no warnings or errors in implementation. And that's, I guess, the important one. So that's kind of one of those things. So yeah, I think all of these problems are relatively manageable. You just have to know about them. But I also don't think you have to know too much more about that. Also, one of the things that I'm finding that I still don't really have a good handle on is how much logic can I actually put between two registers before that's going to become a problem. Because interestingly enough, even with this very basic design, I can actually show this. So if I build this as is, this will just work. But let me do something kind of interesting. So if I kind of model this circuit here with a really simple model, it's easiest to show it if I just draw it. This is my counter. This is my counter. And this is actually, there's 32 bits here. So this is actually 32 1-bit registers sort of in parallel. And so we can do this 31 down to 0 syntax, which you will also see. In fact, you can see that here. And again, this has the D input, and that's 32 bits wide, and it has the Q output, and that's also 32 bits wide. And what I do here is I have a little thing here, which this is 32 bits. And then I have this value here. And I call this counter next, refers to this part of the design here. So essentially I have this thing where I always have this counter that's increasing by 1 every cycle. And this is how you would actually design that, is you have this register, and then this adder here, and then here. So the interesting part is that I also have some logic about when this is going to reset. And what I do is I have that logic here. So I essentially have a mux that's here, and the one input is this, and the other input is 0. And for the input of that mux, the selector here, I have a compare where I have this sort of equals block, and I compare this value to, I know this is getting kind of confusing, but I compare this value to 1,000,000 minus 1, also is a 32-bit value. And so essentially, if the next value is going to be million, so if the current value is 1,000,000 minus 1, then we actually want D to be 0 for the next cycle. Otherwise, we want it to be this adder here. Now, the interesting thing is that this add, because all of this here is going to be like 32 bits wide, and with an adder, you need the high bits are going to depend on the low bits. So you have this really kind of long serial chain. And in fact, if we look at the synthesized, well, I could open the implemented one, but that's fine. Let's open the design. It doesn't matter, it's out of date. If we look at the schematic here, we can see that there's this long chain of all the different bits for the registers and also all the different little adders. So if we look in here, we should see there's all these registers here. And then we also will see all these carry blocks, which are carry adders, from what I can tell. And you can see the inputs, a lot of these carrier ins here are carry ins are just 0 because we're only adding 1. Until the lowest bit, I think, which is probably over here. take 0. Should be somewhere here, and then there's going to be a carry add somewhere around here where that input is tied high. And I kind of want to see it, but it's actually not that important. It's just kind of interesting. Yeah, I'm not sure where it is. It's in here somewhere. Just representing that very lowest bit that we're adding being 1. And in fact, actually, it might even not be that. It might be, looks like there's a logic block here. And this carry comes from this. So it might actually just be a little inverter, which is probably what this LUT is doing here. That's probably what that is actually. Because if you know that the lowest bit is going to be, you're going to add 1 to it, then the carry is going to be 1 if this was 1. And the output is going to be the inverted value of that when you add 1. So it's actually probably that's what this is. But anyway, what's interesting is that another way I could have done this that would have been equivalent is instead of tapping off this value and checking 1,000,000 minus 1, I could have also tapped off this C next and checked for 1,000,000. And that would have been an equivalent circuit. But of course it changes the timing relationships, because then suddenly maybe the input to this bucks is a shorter line, but then maybe this compare is more expensive, or the fact that this compare happens after this add instead of simultaneously with the add. And I think that's kind of the most important thing here, is that if you look at the data dependencies, then we have the add and the compare are both sort of inputs to the mux. So these could actually happen in parallel in the hardware. Whereas if we did the add and the compare, then we'd have this kind of chain with the dependencies, the add, the equality, and the mux. And so clearly this period of time can be shorter than this period of time. Is kind of the important thing. And so if I go in here and I go and change this, so instead of doing lead counter, I'll do my lead counter next is this +1. So if we do lead counter next, and then we need to add 1 to this. 3, 4, 5, 6, 7, 8. Yeah, so it's actually 100 million because this is running at 200 megahertz. So that's what I want. Then I will have created again this scenario. Instead of doing this, now I'm doing this, so I have a longer chain between the two registers. Or actually between the register and itself, which we can think of as 2 registers. Right? It's the same kind of idea. So if I go ahead and build this, I'll run implementation, which should also run synthesis. It'll take a couple minutes, but the point is that then I don't think this meets timing, actually, when I did it the first time. Because that's how I wrote it initially, because it was a bit easier to write. But I think, of course, it's Verilog, so I should also be able to write if the lead counter is this -1. That would have been fine, but already there's kind of a really basic case where you can, by changing the data dependency, you cause a longer signal chain, which means the hardware has to be serial, and that can really matter for timing already, which I think is interesting. Oh, that's a really cool book suggestion. I didn't know about that one. Designing Video Game Hardware in Verilog. Cool. Wonder if that's good. That seems like a good book to own. The other thing that I think you'll find is that like finding tutorial resources in Verilog versus like software it's a lot harder to find really good stuff. But I think it was why can't I remember his name now? Dark Second pointed out HDL bits. Let me find this for you. This was a really good site that was similar to if you played TIS 100 or Shenzhen IO. This kind of gives you a lot of like very simple things to do and problems to solve. So to me, it kind of felt similar to playing one of those games, but it actually teaches you Verilog. So if you go into, and it can remember your progress. You can sign in with an account, or it'll just use cookies. So let's say we have this rotator thing. Go to one of these problems. So here's your module declaration, and it gives you some description of the behavior that you want, and then you need to implement it. So if I just submit this without doing anything, this is going to run online in a version of Quartus, and it's also highlighting a lot of the output for you. And then it gives you this timing diagram that said, here's the inputs, here's the clock, and then this load line, and then this enable and data lines. And you can see that the reference expects this. So you're essentially is trying to load this data when this load is here, but mine doesn't do anything. And so it also gives you this mismatch signal that is high for all the parts where your thing is wrong. And this also has a lot more basic stuff. So this is this rotator thing, but there's also like the very basics. You make simple wires, simple gates. And I think this is a really great way to learn Verilog. But of course, there's also Verilog versus VHDL versus System Verilog, and which one you choose is going to be up to you. There's a lot of Python-based languages as well, but I definitely wouldn't recommend learning one of those unless you learn one of these lower-level languages first, because this is what the tools use. So you're going to have to touch Verilog or VHDL in some form or another, no matter what. So it makes sense to be able to learn to know that. But a lot of these Python HDLs seem really nice, like MeGen or NMeGen. I have my own for XenoWing now, which I'm really happy with, but it's really minimal, and that's kind of why I like it. It doesn't let me screw up, which is nice. But definitely don't need that. But yeah, so I wanted to open this design now, and let's see. So here, if we go to the summary, or actually here, it just opened the reports, and it said right away, timing design, or design timing summary. Big red icon here. It tells me here we have this negative slack, seems to be okay, but here's our total one is pretty high, and the number of failing endpoints. And if we go a little bit farther, we see this intra clock paths, and we see the paths within this named clock, which is called clock. And here we have a bunch of setup violations. So this essentially the signal wasn't stable for long enough before the next clock edge. And we can see a lot of paths here. So in this case, this was my LED counter reg bit 2, and then LED counter reg 29/D. And I don't know what the C and the D is. Not entirely sure. But again, it shows you this path. And it shows you how wrong it was, or how much slack you have. So essentially, the slack is how much wiggle room you have. And then if it's negative, that means you violated it by that much. So if this were to work, you often would have seen, for example, one of these are good paths where the slack is positive. So when it's negative, it's obviously very bad. And if I double click one of these, it will show me, I think it shows me all of the different things that this goes through. So here's the whole data path. You can see it goes through all these different carries, and then a couple LUTs as well. This is a pretty long path. And I think, again, that's because we need to know, because the way I wrote this logic, we need to know the result of that addition and the result of that compare before we can know what the value for this bit is going to be. Yeah, that's what this is. The C is the clear. It's the clear in the data, because the clear input is based on the data output. We don't know if we're going to clear until we've calculated the addition and the other thing. So we see the path there. And the other thing that's really cool too is you'll notice as I click these different paths, we get this highlighted stuff here. And I can go in here on the device and it will show me the path, which is really, really cool. In fact, I think I can click individual parts of the path, and it should show me all these little arrows here. So you can see exactly where in the design this kind of went wrong, which is very cool. So there's a lot of good tools a lot of good tools for kind of analyzing where these problems are, and it will give you a lot of good information. But what's critical to being able to even use these tools at all is making sure your design constraints are correct. If they're not, you will get a lot of like there will be errors in these check timing things, and you'll see like no input delay for something, or unconstrained points, and those are just paths where it can't even do analysis for timing because you haven't specified the constraints properly. So it's critical that you and again, I'm just learning this stuff now. This stuff I've learned in the last couple weeks, but it's critical that you constrain the design properly in order for these tools to be able to work. So if I run this on my device, I don't know what will happen. It'll probably almost work, but it'll be really unstable. But maybe this kind of slack is not that bad for this design as well. Like this might actually be good enough, but we're gonna assume it's not. So there, I think, is an interesting example where I actually want to do. I actually want to do this because I want to try and fix it by doing this literal here, because this literal the compiler should collapse this. And now granted, there are also different optimization options like you can have with a software compiler. In fact, I think in the settings of my project, you can choose how aggressive it is in trying to optimize your design. And it might be actually that could have kind of figured out that if it would have compared that against whatever the value was, -1 or something, that would have been equivalent. I don't know how advanced the optimizers for a lot of this stuff is. But I have a strategy here where it's like the strategy here is just whatever the defaults are. But you can have it explore different options that will try to improve performance, then pick what the best ones are. You can have it do quite a lot of different things. Or explore if you want to optimize for area, or if you want to optimize for power, all kinds of stuff. So there's a lot of things to tweak as well. But of course, in a project that's this simple, it doesn't make sense to change those. But there are options. So there are other things like you can retime your design to try and fix this, because like one way to fix that would be exactly how I had it before, which is just rearrange the data dependencies such that these can be in hardware executed in parallel before this one, and then it works. Another way to do this is if we don't mind if this signal were a cycle late, we could stick registers here. And then that means that now this path has an entire cycle to settle, and this path has an entire cycle to settle. And maybe that's fine. You can also mark a path as being a multi-cycle path and just say that, like, instead of actually adding a register here, just say, well, I'm not even going to look at this input for another 2 cycles. Or instead of in the same cycle, I'm going to wait another cycle before I sample the output here from here. So you'd mark the path between this register and this register as a multi-cycle path that's 2 cycles long. And then it will also kind of lay those out far apart, for example. It can do that. So there's a lot of cool stuff that these tools can do. I actually want to see if I can write this. I probably can. I spent a lot more time just talking about this since I started this stream today, but I think it's fun. So it is more involved, but it's also, I think it's cool. Vowel bus. The board I'm using is a Numato Labs Mimos A7. Before I was using a Intel Max 10 development kit, but I decided to switch boards. Yeah, sorry, Repnop, that you missed a bunch. Yeah, by the way, Dan MP87, I would love to recommend some System Verilog programming books, but admittedly, I don't know any. So maybe I can bug the guys at work about it and forward the information. But I know that those Sunburst papers were really good. And the HDL bits again, that thing seems pretty good. Admittedly, I don't really know that much System Verilog either. The System Verilog that I'm writing is pretty much Verilog with just logic written everywhere instead of reg and wire. And I would like to brush up on that, but yeah. So now I want to open this new design, and this should be fine, I would guess. And now we see no issues with the timing. And we go to the summary, it also says no errors or warnings. So then again, this still had those same these intra clock paths, but then none of them had any issues. So we can see a lot of slack on all these paths. And again, if I go and pick one of these paths, look at the design. Now you can see this path is a lot more linear, which is kind of fun. Whether or not that's what actually helped timing, I'm not sure. But I mean, it makes sense that rearranging it like that would help, again, because of the data dependencies. So yeah, you're absolutely right. This is just slack for the timing between the paths, or for the paths within the chip. You should definitely also look at these the other slack for the external stuff. You're absolutely right. And that, I think, I don't actually know where to check for that yet. Maybe it's these interclock paths, which I don't have any in this design because I marked the only output as a false path because it's just driving an LED. So that's probably that. That's probably that. Who knows? That's cool though. Looks like my reset input's way over here, which makes sense because it's on this particular pin. I wonder what this is too, because you can also like look at what this is. I guess these are IO pads or something. Don't know. But I wanted to. It looks like this. The actual LED registers down here. This is the register that holds the LED state, looks like. So I want to see, like, is it nets that give me this? Yeah, cool. Oh, this is cool. So here's my clock. Oh, man. Look at that. Way into here. You can see what this constant thing is. Here's my reset synchronizer. So here's, I guess this is the output of the synchronizer that goes to all these different registers because all these are going to need to be reset. Other paths here. This is the LED to the output. So I think here, but I know exactly what this is. I think here I just assign the LED as the LED register. So I don't invert this at all. I'm just poking around here at this point, by the way. I haven't looked at this. But it looks like this is probably the input to that LED register. And then the output buff from that register is there. Again, we have the reset here coming in. Looks like that's buffered. Then that goes to the synchronizer. A lot of this stuff. There's that locked signal. Anyway, I think this is pretty cool. Just looking at this. So yeah. Very cool. But yeah, when you're interfacing with external stuff that's actually timing critical, you need to check those slacks. Although again, if you have constraints set for those paths, it should report those if they're going to be problematic. So I guess the message of the day is don't skip learning how to constrain your design. Because that's been a lesson I've definitely learned the hard way the last few weeks. I was hoping to do something more involved today, but I don't really know what. I thought about maybe, because I did download the project for HDMI output for this board. I don't think I ever ran it though. So I guess I can try that. So yeah, so I did build it, but I didn't generate a bitstream or program my device. But with this board, to program it, so it looks like, I have this already implemented design, so I should just be able to click this generate bitstream thing. But it has this particular board comes with this tool called Tanagra, I think you say that, and then it sees that I have my device connected, and I can go program the device. In this case, this is the bitstream from that other project. I'm waiting for this to write this bitstream before I go find that file, which I guess you guys can barely see above my title there. But I want to write this to my board and then check if that HDMI output actually works, which I expect it will, but I haven't tried that yet. So I'm going to hook up my capture card as well so we can see the output while we wait. So maybe I'll be able to see that soon. Need to configure some stuff. Okay, so this finished writing the bitstream up here. So then I'll just go ahead and open up a different file. And I think these end up, I gotta find it again. Runs, I think, and then the impl has this dvid test.bit, which is generated just now, so that's probably it. And then you can have this write to the flash memory, so then the next time you actually start up the device, it'll be there. By the way, this device, if booting from the flash memory, it takes like 5 or 6 seconds to start up, which is not really an issue, but when writing to the SRAM, that happens like instantly. So that programs, this finishes, and then hopefully we get some output. And we do already. Great. Okay, that worked. Always nice to know, or nice to see that when you have an example project, that it actually works out of the box. That makes me happy. Oh. Now my mouse is going crazy, and I don't know why. I hope that's very unrelated. Cool. Now, one of the, I guess, quote unquote downsides is that this example project is in VHDL, which I don't have nearly as much as experience with. So I'm not entirely sure how I'm going to want to break that down. But I just kind of want to poke around here for fun. Look at this anyway. Also, again, the source is here. So there's this dvid test here. And I think, yeah, there's this top level VHDL thing here. And interestingly enough, this has, I think, some more interesting options with this clocking IP, which you guys can't see, I just realized, because the output. Move that out of the way. And so here, they have this input clock, and they're also generating 3 clocks here. and then when they're all locked. So here it looks like the input's going to be 100 megahertz. So that's also probably coming just from the oscillator on the board. And then here, the output clocks, here we have the DVI and the DVI negative, and it looks like what it did here is it said that they're going to be the same rate, but then it shifted one 180 degrees, and I guess that's to get it sort of differential. So when one's high, the other one's low. It's probably what's happening here. And I guess this is to generate the TMDS signals for the HDMI output. I don't actually know because I haven't really looked at this much, but that seems to be what it is. And then it also generates a VGA clock because this actually generates sort of a video signal that's then sent to both outputs. But then hey, Grashev, yeah, this is a different board. But then the pixel clock is all you need for VGA, so it's just 25 megahertz. So this actually generates these designs of multiple clocks. And I also don't think that the VGA output is actually sent anywhere in this particular design. I don't think there's any output for that. But it generates the clocks for it and everything. But again, nothing too fancy here. Again, have the reset and the locked things. Reset is active high. That's fine. All the other parameters there looked pretty basic. And then these different video signals here. There's this TMDS encoder, which has this clock data C blank encoded. I don't know what this means because I haven't really looked at TMDS at all. But I guess this is it. Just does this basic encoding at 125 megahertz, however that works. And then we have the VGA part, which should be quite simple. Because this should just be a bunch of counters, and then whether or not you generate the different active signals, and also I'm guessing there's a data enable signal here. I'm not actually sure. We have H-sync, V-sync, and blank. Sign the outputs. What's R? Is this register here? Looks like it just collects all this. There we go. That's where that's set. Yeah, so that's pretty basic output of this, and then these are all the different timings. So here's the resolution, when the sync signal starts, when it ends, the max count here. Nice thing about generating VGA is you can just look at these very basic counts, and you can find tables for these all over the place. So that's nice. That's the one I expect to be really straightforward. The DVID, which I guess digital video, seems to be a little more complicated, but I don't know if it's that much more complicated. Just clock. Yeah. It seems that this actually takes the same 5x pixel clock pixel, which actually that makes sense because we have a 25 megahertz pixel clock for the VGA part. Actually, yeah, so I think what's happening here is this VGA portion here is being fed into this digital video portion here. We have red P here, for example, and this looks like it's being mapped to red, which is here, and then that is a sign from this VGA one. Yeah, so they're using this VGA generator to just generate like a generic VGA signal, and then they encode the TMDS outputs, which is probably just encoding individual bytes for this. And it looks like I don't see anything related to like crossing clock domains or anything. And so I'm wondering if this clocking module is actually generating clocks that are in phase enough that it can understand those relationships and make sure that passing data between those domains is actually okay. Because it does have this phase alignment thing here. So maybe this is enough in this case. I actually don't know. I wouldn't have assumed that was safe, but that might just be me being paranoid. But then it makes sense that the pixel clock is 25 megahertz, and then we have 125 megahertz for for the TMDS encoding, which I think it mentioned in here. Clock and clock end should be 5 times the pixel clock. Also, this guy who wrote this example has his email here, so maybe I'll email him actually and ask him. That'd be fun. Seems like a good idea. There's this shift clock. I don't know. So this is SR type equals async. I wonder if that's like a latch thing. Again, I don't really know enough VHDL to really understand that. So what I'll probably do at some point, and probably not today because I'm getting pretty tired, but I think I'm gonna just look up how TMDS encoding works, because I mean obviously I can just use this VHDL code as is, except unless there's licensing constraints with that. But like, my point is I could just use an off-the-shelf one as long as I clocked everything right. I wouldn't worry about it. But I'm really interested in how this works, so I'm probably going to look up TMDS encoding in general and kind of figure out, like, if I can find like a description of that kind of protocol and something that can describe how this encoding works, and then cross-reference that with this code. I think that's the most fruitful way to try and understand this. And I think I am going to send this guy an email. What's the worst that can happen? But yeah, I think the sort of next steps for the Xenowing project in terms of getting it up and running on this board is again making these really tiny projects that just sort of test different parts of the board. So I've tested, like, I can blink an LED. That's really easy. I've tested the clocking, so I was able to adjust that at different rates and adjust my counters, and the LED still blinked very clearly at 1 period a second. So that was nice. I haven't really tested much of the other outputs on the board because, I mean, like, there's what, 8 LEDs, and they're all going to work the same, and there's a bunch of switches, which that's also going to work the same. Like, the documentation for the board is pretty good about that stuff, so about how all that's connected. There's also some 8-segment displays, which maybe I might want to hook up now, because that might be useful for debugging or something. Just some basic system state. In fact, one of the things I was thinking about anyway is having a really small sort of CPU and memory and everything that's just like a board management controller kind of thing, where I could have it like monitoring the monitor sense, for example. So if the monitor gets unplugged, we can have the controller sort of sit there and try and pull and bring that back up. But I actually don't know if we'll get those sense lines through these HDMI connectors. Probably we do. I don't know. We'll see. That's actually another interesting thing here, is that it looks like the only things that are hooked up for this, if we look at the top level ports here, the only things that are hooked up, I think, is the input clock, and there's these data outputs here, which I guess is the output of the TMDS stuff. These are, of course, 3 bits each, it looks like. So I guess this would be 3 differential pairs, if I'm reading this correctly. And then these are differential signals. And then there's the output clock, which also are differential, and then the input reset. And that's kind of it. So there doesn't seem to be, like, I know HDMI also has some I2C stuff where you can query what kind of monitor is connected, what kind of resolutions it supports, all that kind of stuff. I think VGA has that too, generally. But it looks like you don't need that, is what I'm gathering from this. So, yeah, that's probably a really good idea, Daniel Colin, or at least like the Mega Blaze Vivado, whatever, the whatever Xilinx has. It seems that Mega Blaze is their sort of general soft CPU core, which depending on if it gives you like a nice compiler for it might be smart, because then it would at least be really easy to generate that IP and probably generate the IP that works with that. For example, the Ethernet controller, or whatever else you might need. But I don't know what that's going to look like to make kind of like a slave Ethernet device. So there might be something useful there. But also risc-v is cool, so not to deter you from risc-v. I'm just trying to enumerate more options that are probably going to be easier, but who knows? As I find that project you're doing really interesting. So it seems that the Mega Blaze is kind of Xilinx's soft CPU, and I think Intel has NIOS, it's called. But I never used any of that. But also, this board has the Numato website has an example with a Mega Blaze setup that does hook up to the memory. It hooks up to the Ethernet, hooks up to a bunch of stuff. So it's kind of a full embedded platform. I'm guessing it also supports the UART, which is another thing that's that I need to test for the Xenowing, because obviously I use that for debug output, but I also use that for code reloading. So getting set up with that and making sure that I can still read and write over the UART while still having the board be programmable is going to be interesting. Because my guess is that the FTDI chip that's on this that does the UART to USB conversion and everything on this board is a lot more advanced than the one that was on my other board. And so on this board, it's also hooked up so that that's the way you program the device, unless you have like an external JTAG cable. And it seems that there's multiple channels that it supports. And I don't know if those are all hooked up or if one of the channel ends up being dedicated to programming the device. So it might be that if I want to use that for my design, I actually need to get another programming cable. I don't think that's the case. I need to look into that more. That's just something I need to explore. But that Mega Blaze example project, at least that's probably the most complete example that I think comes with this kit, which I would also like to set up at one point just to see what it's like to use that. But I'm guessing it wouldn't be too bad. So, but yeah, this looks like it's pretty straightforward actually, and it is nice again to know that we may not have to do anything else for the video output here. But one of the things I do also want to look at is the constraints for this, because this is another example where also some simulation stuff, which is kind of cool. I'm also kind of curious about that. Maybe that's just generated stuff. Anyway. This has constraints on these outputs again, and actually it doesn't seem to have any timing constraints set here, which is kind of interesting. And in fact, if we go to I would have expected to see those there because the timing is going to be somewhat important here. But you can see one of the nice things about these design constraints files in Xilinx or in the Xilinx tooling is that you specify both the pin that you're going to be connecting to, as well as this IO standard, and then where it's hooked up in your design, as well as whatever like timing constraints it has, kind of all in one place. Whereas I think you can do the same in the Altera or the Intel tooling, or in Quartus, but I ended up doing it where I was using the pin planner to match the pins, and then the constraints were elsewhere. So, oh hey. Grochev, awesome catch, by the way. I don't know how I missed that, but I think you're absolutely right that there's this TMDS 3.3, which I'm guessing is 3.3 volts. So this IO standard just saying that it's TMDS 3.3 is probably enough to do the timing, because the system would know the clock you're running it at, and it would know that if this is the IO standard, maybe that's enough. In fact, a nice way to check is we see no errors or warnings here. And again, we can look at the timing summary here. We do see that we have some unconstrained paths here. It says here, or at least these don't have output delays, and it says that there's a high severity there. So maybe that's something we want to look into. Um, I don't really know what these should be if I were to set the output delay, so I'm kind of curious to look into that. By the way, I just noticed this is still in the way, but what I want to show is this big thing that's yelling at me here, which is important. And you see a little icon there. So generally in this check timing thing here, general information, we seem to be fine. But then here, this summary, here's our different clocks. And here we have, in this check timing one, the worst severity is high, and that's this no output delay thing, and there's 4 of those. But for all the paths, looks like everything's fine. For example, this DVI clocking thing, we have these set up and hold, and everything's nice, everything's great, except those no output delay paths. I bet, Grachev. I don't like that, but it seems to be so normal with this stuff. Again, some synthesis warnings seem to be fine. Whatever, I guess. And I think this reset just goes to the clocking stuff. I don't know if it's actually used in this design. It might be used in the in this digital video or the VGA parts. Actually, do we even have reset hooked up here? No, we don't. So, I mean, that's fine. Like, what's going to happen is that I'm guessing there are some counters in here. So it's like there's this shift clock thing. Because here, beginning of the rising edge of the clock. The shift clock is whatever this shift thing is. And then it latches values like this. It might also be that there's this sort of initial value. And again, because this is for FPGA, you might not need those resets. But I think you do need the resets for the clocking module. So that's probably why that's there. Honestly, I don't know. Maybe I'll ask this guy in the email what the deal there is. These are probably very basic questions, but they're still questions that I have. And again, this VGA thing doesn't have those either. It does have the pixel clock, and I'm guessing it has these internal counters here, which is what these are here. Yeah. H counter and the V counter here. So technically, I mean, these could start at anything, but I think the initial values are given here. But there's no explicit reset here, which again is probably fine, because I think on the FPGA, if you just configure, it's going to be what you expect. And then I bet if I bang on the reset button here, it disables the clocks. So that's why you see when I push the button, like now, the signal goes away, but then when I release it, it comes back. And I'm guessing this state just isn't affected because it's not reset. So in fact, the clock is going to stop. The output clock at least. So, but these registers probably still hold their value. And it might also be too that I mean, the logic here is so simple, and when these counters reset, it's so simple too, that they might just end up being back in sync after a while, even if they're wrong. So it's a very simple design here. But I read about that too, that it's often that if you're targeting an FPGA, it's sometimes a good idea to just not have resets, because the resets will oh, I just realized who Finrog was. That's my future brother-in-law. That's super funny. He's probably gone by now. Anyway. Yeah, those routing those resets, as we saw from the simple LED thing that I had, where I had the reset and it was kind of fanned out, like that's using routing resources that maybe we don't need. So I would still like to support a reset for the design. If nothing else, just so that I can push the button to reset, which I think is nice. I don't like, this is a small project, so it's never going to make it to an ASIC, but just seems like a good idea to have those resets like that. Because also these initial values would hold in a simulator too, so that should be fine. So maybe I don't need those, but I think I'll still work with those unless they become an issue. But yeah, this was at least interesting to see that that we could like encode this TMDS value with a clock that had the same phase as the pixel clock. At least it seems like that. I'll get that clarified. Because what I'm thinking in the Xenowing is that I want to have the CPU be at like 100 megahertz or 200 megahertz. Whatever ends up working. Like I just see what the memory interface is going to look like first. So I'll have to work through that in another test project. And once that's all figured out, then maybe I'll clock that to match that, or do do a different clock domain for the main design. I'm not entirely sure, but I'm thinking that the main design is going to be like I was thinking like 100 200 megahertz, which is very easy to get that down to 25, or at least to have output signals that'll be like output a pixel clock, at least a register that outputs a pixel clock that's going to be at 25 megahertz, because then you just have a counter that counts up to 8 whenever it's 0, for example. You or at least if it's in like the low 4 values, you make it high, otherwise you make it low. So you just take the high bit, for example, which would give you the other way, but it doesn't really matter. That's a really easy thing to do. And then like that's actually what I did in the existing design. Is right now it runs at 100 megahertz, and then every 4 clocks, then I change the output values, and then I take the high bit for the pixel clock output. And I guess if I read this correctly, then I think this pixel clock, yeah, this registers all those in the next one here. If I have a clock that's say 200 megahertz and it's phase adjusted such that this 125 megahertz signal matches, it might be safe. I don't think so though. I'll have to check that. It might be that what I end up doing is outputting the video signal and everything from, again, the 200 megahertz domain or whatever. And then having another part of my design that's based on this pixel clock that should be in phase with that. Yeah, I'm actually not sure. I need to think about that one a bit. It may even be that just to match this clock, we end up running the design at like 125 megahertz and do the TMDS within that domain. I'm really not sure. I need to think about that. And again, need to find out what the memory controller interface that we get is going to be clocked at. Because I don't know how much freedom we're going to have with this board in terms of, can we do a half rate interface? Can we do a quarter rate interface? Because I think from the example that I saw, this we're going to end up running this memory at 400 megahertz. And a half rate interface from that is 200 megahertz, which sounds like a nice speed to target for our system, but I don't even care. Like if our system runs at 50 megahertz, it's still going to do what I want it to do and make me happy. So, but probably 100 or whatever is what I actually want. And then if that ends up being 125 to play nicely with the TMDS output, that's probably cool. Really depends. But the important thing is that we need to do this TMDS encoding ourselves. So that's going to be important. But I might even just do 2 clock domains where I'm doing one from the main system that's going to be outputting essentially a bunch of these signals that are only going to change at 25 megahertz, even though I'm clocking that part of the design at 200 or whatever megahertz, just like I did with the Xenowing on the other board, and then have another part of my design that's running at, for example, 125 megahertz that's just careful about when it samples those inputs and has some of those synchronizer chains and everything. Yeah, again, have to think about it, but I think that'll be fun. But I think what I'll do before that is make my own version of this HDMI output just to learn it, and also just drive this in my own test project. Get rid of all these warnings and make it nice and clean. But I'm not going to do that tonight, because I'm tired and I think I want to be done streaming. But anyway, that's kind of a project update. I've migrated to this board, and I expect things are going to be a little bit easier for us. The board seems to be a little bit better supported. It's a bit newer. I think we have a little more logic elements, but it's also new. Like, I've never used Vivado before this, so lots of stuff to pick up. And again, these very small projects about kind of targeting each one of these little pieces of the board that we need are going to at least help me learn a lot of this, which is really nice. So the next little while for the Xenowing is going to be kind of bring up on this new board. And eventually, if we end up having the same kind of issues, then I'm going to get really frustrated, and maybe we'll be able to fix it, and then maybe I can even fix it on both boards, which I actually would be interested in doing if I could guarantee that I could. But probably not because of that issue with Quartus where I couldn't regenerate the memory controller, because that got really annoying trying to go back and forth between my laptop and my main machine. It was okay for simple tests when I just like had to try stuff out, but those tests weren't fruitful anyway, so I don't want to deal with that anymore. And this design is not that important that those are the kind of things I want to like fight through. I can always clock my design down and use FIFOs if the memory controller needs to be stuck. Also, I don't know if we can do, I think it's called hierarchical design in the Xilinx tools, but essentially the design partitioning to say like, I want the memory controller in this block, and then I want the main system in this block. And then you can have it so that you treat those specific units as like black boxes, so that the Xilinx tools will not recompile those, which can save a lot of time. But also, if it's difficult to close timing on one of those parts of the design, then you're not changing the parameters that actually made that timing work every time you change the rest of the design, like something unrelated. So might be nice to explore that, but I don't know if the free tier has those. And another big thing that I need to look into, which I don't think I have on this board, but maybe, is the ability to use chip scope. Because all the programming again happens over this USB interface, and so I don't think that I have a way to get at JTAG or whatever chip scope needs to be able to talk to the device like that. That's something I need to look into, because at least when using the Altera board, the equivalent features signal tap, where you're adding this like logic debugger to your design, and it handles all the plumbing associated with that for you. Is extremely helpful to be able to actually see what's going on in there. So I would love to have that feature. It's not a deal breaker, but if I need to buy a somewhat expensive cable to do that on whatever Xilinx boards I end up buying, I'm going to do that because it makes a lot of sense. It's an FT232. Oh, is that used for JTAG? That's really good to know. It's an FT232-2H, I think, by the way, which I'm guessing, since that's a beefier version of the 232H, I'm guessing that also still supports JTAG, which is great, and that probably explains why I'm able to program the board with it in the first place. But that makes me hopeful. So good. I'm glad you pointed that out. JTAG and UART seems to be used for. And I guess that's probably why they used a chip with multiple channels, so that you could do UART with it and do JTAG programming with it. That's probably the idea. Also, a little bit more of what's kind of swirling around in my head. I'm really inspired by working at a hardware company, which is why I'm working on this in the first place. But also, we had some good presentations by our hardware lead recently, where they were talking about the very large projects that we make in our office, and I was really inspired to even just do some like basic schematic design and board layout, which for something like this, I don't actually think would be terribly difficult, because again, we have schematics and board layout files for this exact board. So what I'm thinking is that whatever subset I end up using of this board, I might try to recreate in my own schematic and then look at the board layout and see like what I actually need. And there's this, I'll probably ask a bunch of you guys, because I think a few of you guys have a lot of this experience as well. Can maybe look that over if I end up even doing that, but I just kind of want to. It's kind of cool. But there's a subreddit which I think is called Rate My PCB or something, and people will just post PCB designs, and then people go and kind of tear it apart, which is really cool. It's a really great opportunity to learn. So maybe I'll post it there. Yeah, exactly, Daniel Colliner. There's the yeah, that one's not that expensive, which is nice. Exactly, the platform cable thing. Yeah, that's exactly what I'm hoping I don't need, but that I would buy if I found that I did need. That's exactly it. But I'll do more research on that. Krichef said, any ideas for the case designs yet? I have a few ideas, but we'll see. One of the really annoying things about the case design too is that I'm really picky about like materials. So you want PCB printer? Oh, that's really cool. $5,000. That's actually nothing for this. Oh, that looks really cool. Man, home manufacturing is going to be really interesting the next couple of years. I think it was 2013 where I really wanted to make my own handheld game console. That's where all this kind of started, by the way, in my head. And what I wanted to do is this is before I started streaming, but I actually wanted to like make videos of like the whole process, not necessarily stream them was what I was thinking at the time, but just to kind of capture that whole process. Now I think a lot of that's unrealistic to capture everything, but at least a lot of it. But anyway, at that point, I just wanted to do like a system on chip and just do some basic board design and case design and kind of figure that out. Because I had just bought a Nintendo 3DS and was really inspired by that. But what I really wanted to do at that time was also explore home manufacturing. Like I at that point, I was convinced that I wouldn't be able to make a board, which I'm excited now because it looks like those kind of products are starting to come out as well, where you can actually make more advanced PCBs at home as well. But again, the point is that like the technologies I want to explore then were home reflow and doing all that, which right now still scares the crap out of me with some of these BGA packages and stuff. But that, and then 3D printing for the case and all that stuff. And so it excites me that like at the time I decided not to do that because I didn't think I was ready to kind of go through all of the failure involved with setting all that up, because it's still in its infancy, this kind of home manufacturing when you're doing relatively complicated stuff. But I'm glad I waited, because now I'm doing FPGA stuff, which is kind of more interesting for that kind of project anyway, because eventually I would love to have a handheld Xenowing, but if that ever becomes a thing, there's a lot of factors there. I don't know if that's even something I'm going to want by the time I get the project to a point where it makes sense to even look at designing a board, but it's kind of cool. But anyway, I would love to, in my lifetime, be able to manufacture something like that entirely at home. And I find that really exciting. And like $5,000 is nothing for that kind of product. Obviously that's expensive, and if I'm only going to make one design, then it doesn't really make sense. But like my point is, it's actually incredible that things are getting that cheap. That said, I'm very skeptical about how well something like that can actually work. But in the next couple decades, that kind of home manufacturing is going to be really, really cool. And I'm very excited about that. But in the meantime, we're going to get the Xenowing working on the new board. And it's very realistic that what I will end up doing is kind of playing with no, Drew, that's not how I met her. I met her at a big LAN party called The Gathering many years ago. Yeah, I would love to be able to make my own ASIC at home too. And you know what? I think in a few years we're going to see that too. I think we'll see that at least for like micron level designs. Maybe bigger, but I do think that we'll see ASIC manufacturing in the home eventually. It may not look like that though. It might just be that something like a PCB printer can just be small enough that what we consider ASICs now, maybe we'll have really big chips or something. Who knows what that technology is going to look like in the future. But I would love to do ASICs at home. Yeah, that's very true. Yeah, the cost of the mask and the synopsis tool. Yeah, I think that makes so much sense. 3D printer and copper tape, like that's cool that he developed that himself. When you said it, it sounded so natural, like that was, oh, of course that's a thing. But extra props for him inventing that or developing that. And that makes so much sense though. But there's no way that that's like fine enough to be able to do like an FPGA design for. At least not yet. Like those kind of techniques will totally be the way we do that in a couple of years. But yeah, it's amazing that he did that. Not to take away from that. I just think that's really cool. Yeah, I would love to download and print a C64. But yeah, what I was gonna say is that getting the Xenowing to work on this board is like the next thing, so we get kind of feature parity to where we were before, but then on this board, and hopefully then we continue with the GPU, which is the next thing I want to do. And then I've been thinking about if I want to actually do a controller for it, because I mean you can't really have a game console without a controller. But I've been thinking that a controller, a lot of that is based on like physical design and how that's gonna feel in your hands and the materials and stuff. And I'm not that familiar with like even laser cutting or 3D printing or anything, and I don't want to dive into that yet. So I'm thinking that I'll probably interface with an existing controller design, for example, Super Nintendo or something relatively simple that I know I can work with. And since this board has a lot of GPIOs, it should be pretty easy to get that working. And plus, I already have like level shifters and stuff laying around, so I don't expect that to be terribly difficult to do. And then I might, if I get that working, then I might actually look into like what is kind of the cheapest, simplest way I can do a case. And then it might be laser cutting at the local hackerspace, which is not my favorite choice. I would love to have something that would be a little more high quality than that, but at least then I would get to something that I could hold. And there's also other things about this, like with this particular board, all the peripherals are kind of on the edge, but there's only a few of those that I would actually use. So I'd probably use like adapters and stuff to kind of like break out just the parts that I would actually use, and make a different power switch, all that kind of stuff. So there's probably, yeah, cardboard would be a lot cheaper. That's very true. Maybe I'll prototype it that way. So just something to kind of make it like real, but I think I would build it around this board is kind of also the point that I'm getting at, is that for the first iteration, just don't use a custom board. Because the other thing too is like, how much would it cost to do a custom board that has everything that this board has on it but less stuff? And at the end of the day, I still think that's going to cost me a few $100. by the time I get the FPGA on it, by the time I get all the peripherals that I need, by the time I've ordered those to whatever PCB manufacturer and gotten the PCB made. Like, I don't think it's that expensive to get a PCB made anymore, but to get it populated and everything with relatively expensive parts, and considering the fact that I would probably fail a couple times before it actually worked, I think I'm looking at more than the cost of another one of these boards. So if I'm really happy with this particular board, then I'll just buy another one if I want to have that separate from the Xenowing project, or not. I don't know. So I'm kind of thinking that these days, even though I do want to design my own board. So we'll see how far I want to go with this. But right now I'm enjoying thinking about that stuff. Anyway, I am totally going to watch that video, Drew, too. I am very interested in that. Looks really cool. But for now, I'm going to go. And thank you guys for hanging out, and I will see you next time.